Okay, so welcome back. Today we're going to be talking about section 4.5, and the title is going to be curve sketching. So the idea here with curve sketching is, what if I give you a function and I say, without your graphing calculator, graph this function. If it's a polynomial, you might be able to just do it based off of what you know from pre-calc, but you can have other weird stuff like y equals natural log of x over square root of x squared minus 1. That's not your typical function that you would look at, so that one might be a little bit more challenging and one that you're not quite used to. So, in this section we're going to talk about, well, how do we approach graphing this? And this is going to utilize just different methods that we've encountered, both in like algebra 2 and pre-calc, as well as in calculus. So if we start with a function, so we're going to start with y equals, start with a polynomial, 1/5 x to the 5th minus 8/3 x cubed plus 16x. Given this, there's a couple things we could start to look at. And already on this screen, one of the things we could look at is, well, part A, what's the domain? This is a algebra 2 question. The domain you would have here, well, it's a polynomial. There's no division by 0 that can happen. There's no roots anywhere. There's no natural logs. So the domain is everything. Basically, what x values are you allowed to put in? And there's no limitations, so we're good there. So that's one of the ways you could start, is by, well, what x values can I put in? What's the domain? Another thing you could do is you could say, well, what are the intercepts? If I'm graphing a function, intercepts are something that is good information to have, because it tells us, well, hey, what are some specific points? So you could get the y-intercept by setting function equal to 0 with, or you can get the y-intercept by plugging in 0 for x. And you get 0. So that means I'll label it down here as int for intercept. One of the intercepts you get is 0, 0, where you see x value 0, y value 0. You can also find the other intercepts, which are by setting y equals 0. So you have this function. You set this equal to 0. And you can find that. For the purpose of this video, we're not specifically going to find those ones, because we're just going to use this one intercept. But what you could do is you could factor out an x, and then you have an x to the fourth and an x squared, so you could do some sort of factoring things, and it should work out. Now the next part you could do is you could look at what is the symmetry. That was the whole even and odd thing that you may have talked about, where an even means even function is going to be f of negative x equals f of x, versus an odd function, f of negative x equals negative f of x. Now, if I'm asking you on a problem to sketch the curve, symmetry is not an essential thing that you need to do. I will not necessarily require you to use symmetry, but in this case it works out. So if you do y, and I'll put parentheses, negative x, you get 1/5 negative x to the 5th minus 8/3 negative x cubed plus 16 negative x. And all those are odd powers, so the negatives pull through. And then you can factor out a negative, and what you're left inside is y. So y of x. So what do you get? That this is an odd function. Now functions are not required to be even or odd, but this one just so happens to be odd. Okay. Well, what else could we talk about? Well, we can also talk about are there any asymptotes? Now this is back in chapter 2. Recall that a vertical asymptote is undefined at some x value with the limit as x goes to a from the right or left is plus or minus infinity. So basically, for those types of vertical asymptotes in this function, we want to think, is there anywhere where it's undefined? But the domain is everything, so you can't have any vertical asymptotes. Right, it's defined everywhere. But there are other asymptotes. Like, for example, we talked about horizontal asymptotes. You just take the limit as x goes to infinity and as x goes to minus infinity. Now this one will be easy enough. Remember, this is a polynomial. An odd degree polynomial, x goes to infinity will go to infinity, and negative infinity will go to negative infinity. If this was so if the highest power was x to the 4th, for example, some sort of even number, then both of them you would have to look at the sign out front. And in this case, because it's odd with a positive out front, you get that these two things happen. But since those are infinite, it's nice we have no horizontal asymptotes. Another type of asymptote you can talk about here is slant asymptotes. If you're not familiar with slant asymptotes, don't worry about them too much. Just know that there is another type of asymptote that does exist. Okay, so what else could we do? Talk about local extreme values. And the intervals where they're increasing and decreasing. This is just, well, let's do the first derivative test. Do the first derivative test on this. We need to take the first derivative, so that's x to the fourth minus 8x squared plus 16. That's defined everywhere, so we need to just set that equal to 0 and solve. Can factor, and this is going to be x squared minus 4 quantity squared equals 0. So that is x squared minus 4 equals 0, or we have critical numbers of x equals plus or minus 2. Just by adding 4 over and taking the square roots. So we can make our little chart, -2 and +2, and you could choose x equals 3, x equals 0, and x equals -3. You plug those in to y prime, and so the notice that if you just plug in 0, you'll get 16, which is positive. And for the other two, it'll be -3 to the fourth minus 8 times -3 squared plus 16, which is going to be a positive 25. And then if instead you do plug in 3, so that's 3 to the fourth minus 8 times 3 squared, or 9, plus 16, you're going to also get positive. So this thing is increasing everywhere. It stops slightly at -2 and 2, but there is actually no extreme values, no local maximums or minimums. But our intervals of increasing, we get -∞, -2, and -2, 2, and to infinity, with no intervals of decreasing. Okay. And then the next part that we can look at, going along the same vein, is concavity. So that requires using the concavity test. So let's get rid of our first derivative test stuff we have here. And take the second derivative, we get 4x cubed minus 16x. That's defined everywhere, so we set it equal to 0 to get possible inflection points. So x, 4x squared minus 16 equals 0. So that gives us x equals 0. And this, solving for it, you have 4x squared equals 16, x squared equals 4, or x equals plus or minus 2. Okay, so we could test these. -2, 0, 2, choosing x equals -1, x equals 1, x equals 3, and x equals -3. And we're plugging those in to 4x cubed minus 16x. So You plug in negative 3 into there, you'll get negative 60. So that's a negative sign there. Plug in negative 1, and you'll get 4 minus 16. It will be, well, negative 4 minus 16 times negative 1 gives us a positive number, versus if you plug in 1, you get 4 times 1 minus 16 is going to be negative. And then you plug in 3, and you get positive 60. So that gives us our concavity. That we have it concave up from negative 2 to 0 and 2 to infinity, versus concave down from negative infinity to negative 2 and 0 to 2. Okay, so we can start to plot this. So first of all, let me erase this here. The point that kept showing up that we had here was this whole x value of negative 2, well, plus and minus 2. So let's at least see what, if we plugged in into y, negative 2, and positive 2, what values we would get there. So just plugging into the calculator and using the table function, you'll get that negative 2 is negative 17.07, and positive 2 is 17.067 approximately. It cut it off how much, but it's approximately where it is. And I just used this preset scale, but let's make this a 20 and a 10. And let's also drag this up a little. And a negative 20, but keep the other scale the same. Now notice it's not decreasing at all. It will always either be increasing or staying level. We have the point 0, 0. That was from our intercept. We have that it's an odd function. We know that if you look at the x value of negative 2, you're going to be down here, negative 17, which is somewhere around here, just below negative 17. So this is going to be a point. Similarly, you could look at 2 and then 17.07 approximately. So that's up there. You know that it's going to be increasing, domains everything, and it's odd and concave up, so it's going to be something like this sort of picture where, look, so we have concave down, negative infinity to 2, it switches the concave up before it gets the 0, and then it's concave down before going to negative 2, and then concave up, going up. So that's approximately what this would look like, this polynomial. Okay. So now that we have that one, let's do one more example. Once I erase all these. Let's look at a rational function. So let's look at y equals x over x minus 1. Notice if you want to look at the intercepts, the only intercept here will be 0, 0. You can verify that by either plugging in 0 for x or setting y equals 0. But using algebra, that's pretty straightforward that 0, 0 is the only one, because plugging 0 in for x, you get 0. And then setting this equal to 0, you get x is equal to 0 by multiplying x minus 1 to both sides. So the only time where it will cross the axis is at that point 0, 0, the origin. Okay, so let's remember what we had. Before we continue on, let's talk about what is the domain. Oh, sorry about that. Of x over x minus 1. Well, for the domain, we can't divide by 0. So that means x minus 1 cannot be equal to 0. In other words, x cannot be 1. So our domain is going to be everything except for 1. Okay. And then you could look at the symmetry. We're not going to for this problem, just for the sake of time. But the next thing after symmetry we could look at is asymptotes. What asymptotes do we have? So you could talk about vertical asymptotes and horizontal asymptotes. For vertical asymptotes, you want to look, is there anywhere where the function is not defined? There is, x equals 1. So you could look at, just check, what is this limit? And we did limits like this before, back in chapter 2, but notice that they're easier now. You don't have to do it by table, because, well, first of all, we'll get 1 over 0, which this is going to be either plus or minus infinity. We don't really care which one, because remember, horizontal asymptotes will give you, that's plus or minus infinity. What we will, and then the reason we don't really care which one this is because which one it will be will show whenever we talk about what the increasing and decreasing are. But we just know that at x equals 1, there's a vertical asymptote. So let me just put that by a dotted line. Okay, what about the horizontal asymptote? Well, something I've mentioned before is with rational functions, you only have to take the limit as x goes to infinity. Because the other one will be the same just by the fact that it's a rational function. Well, this is infinity over infinity. So you could do this by table, but a quicker way to do this is use L'Hopital's rule. Because you have the indeterminate form infinity over infinity, take the derivative of the top, you get 1. Derivative of the bottom gives 1. And that leaves you with 1. So y equals 1 is a horizontal asymptote. Okay, what do we do after asymptotes? We look at the local extreme values and increasing, decreasing. Okay, so that requires us to find the first derivative. So that's quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. Or what you get is by distributing x minus 1 minus x over x squared, or x minus 1 quantity squared, which is negative 1 over x minus 1 squared. Now that is never equal to 0, right? Because the numerator is just negative 1. However, the denominator will give us where it's undefined, which is a critical number, where x minus 1 squared equals 0. That is, x equals 1. Now we know that that's not going to be a local extreme value, because remember, x equals 1 is not in our going to be in our domain. So there's no local extreme values, but we can look at increasing and decreasing. And you can plug in numbers. So this is a critical value, so we could still do 1, and you would still want to choose, say, x equals 0 and x equals 2. But if you think about it, you're plugging it into negative 1 over quantity x minus 1 squared. The top is always negative, the numerator is always negative, and the denominator you're squaring, so you'll always get positive. So in both cases, this will be a negative number, which you can verify using a calculator. So increasing, none, decreasing, negative infinity, 1, union 1, infinity. That is the entire domain. The last thing we need to talk about is concavity. So we have that negative 1 over x minus 1 quantity squared is our first derivative. And we just need to find what the second derivative is. And well, this thing you could rewrite as negative 1 x minus 1 to the negative second power. And so we use the power rule with the chain rule. Bring the exponent down, you get a positive 2 x minus 1 to the negative 3 power times the derivative of the inside is just 1, or 2 over x minus 1 cubed. Again, that's never equal to 0. But it is undefined at 1. So the possible inflection points is x equals 1. For the same reason, you're solving x minus 1 cubed equals 0. So for testing inflection, you have 1, you have x equals 0, x equals 2. If you plug in 0 into this equation, you'll get 2 over negative 1, which is negative, versus plugging 2 in, you'll get 2 over 1, which is positive. So the concave up is going to be on that negative infinity to 1, whereas concave down is going to be 1 to infinity. So we can draw this now. And so I already put our point down. Recall it's going to be decreasing, which means it's going to be going to negative infinity. So it's something like this and it's concave up, so sort of it's going to be sort of upward parabola shape, going to there and going up with, well, let me erase that there a little bit. With going towards 1, that vertical asymptote. Whereas on the right is going to be concave down. And heading towards -1. So that's how these work. How these work is that you just find all the information that we have here, and then you sketch the curve that we have. So if there's any questions, just leave comments. If not, I'll see you tomorrow for 1 or 2 more examples.